All right, let's start with our very first problem, which is to check for primality of a number. Let's say we have a positive number n. It is an integer, and we want to find out if this number is a prime number or not a prime number. Now, remember, prime numbers are those numbers which have only two factors, 1 and the number itself. So, as an example, 29 is a prime number because look, there's only two factors, 1 and 29. 1033 is a prime number because again it has only two factors, 1 and 1033. On the other hand, 24, for example, is not a prime because it has many factors, 2, 3, 4, 6, 12, and so on. It turns out, in fact, that there's only one even number that is prime, and that number is 2. No other even number is prime, and you can see that very clearly because every other even number is a multiple of 2. Now, the question we ask ourselves is, look, if I give you a number n, how can I find out if this number is prime or not? So how can I solve this problem? Well, the first thought or the naive method that comes to my mind is, look, I know that this number is prime if it has only two factors, which means I can try dividing this number by all numbers starting from 2. So 2, 3, 4, 5, all the way to, let's say, n minus 1. So all numbers that are smaller than this number being tested. If you find a factor, then declare it's not a prime. If you do not find any factors, then declare it's a prime. This is a correct algorithm. This is going to work. The code for this will look something like this. In fact, we are going to do this now and convince ourselves that this is the right algorithm. Briefly, I'll run you through this. Remember, I'm saying, okay, look, this is a function I'm defining. So is prime, I pass in an argument n. This is assumed to be a positive integer more than 2. So I can, put a comment because with 2, it kind of like fails here, right? So it's assumed this is n is more than 2. So I just set a variable result. I run a for loop in range 2 n. Remember, this would be starting at 2, going in steps of 1 all the way till n, but not touching n, which means it will be 2, 3, 4, all the way until n minus 1. I ask myself if n modulo kk is 0. Remember, modulo is a remainder. So, if n, when I divide by kk, if I end up with a 0 remainder, it means that this kk divides n, which in turn means that the number is not a prime number. I make result to false and I break. In fact, I could have just used a return over here. That will also, it could have returned result over here. That's also fine. But this break is important. We'll talk about this in a moment. Otherwise, I just return result. So you can imagine that this loop is going to run, say, 2 until n minus 1. Every number is being checked, and every number, the moment I find that there is a factor, I just break out. That seems to make sense, right? This algorithm is correct. Is it efficient? Can we quantify this? But first, let's convince ourselves that this algorithm is indeed correct, right? So I get to my Google Colab environment. I have created a notebook here, to demonstrate this whole thing. So let me just put a small comment over here saying that, look, say naive, let's say, algorithm for determining a prime, determining, say, primality. So whether a number is prime or not. And for that, purpose, I start putting my code over here. So remember, this is a new cell, which is a code cell, which I'll be able to run later on, just like regular Python. So I just define a new function. So I just go and say def, let's say, is prime. That's the name of a function. I pass in an argument n. This is an integer, a positive integer, assumed, let's say, more than 2. So n greater than 2. Positive integer. Of course, it's greater than 2. It has to be positive. So that's my n. I pass this in and I run a for loop in, say, kk in range. Kk in range 2 to n. Remember, this includes 2 but does not include n. So I check until n minus 1, which is logical. And once I find that there's a factor, so I know that by looking at the modulo. So if n modulo kk is equal to 0, it means this is a factor. I just declare result to false. Before this, I should declare result to true. And I just break, right? So here I just go and return result. So be careful with the indentations. That's important. I mean, this is basically exactly regular Python, right? So remember, all the rules of syntax apply. Just like we have been used to. So here I just define a variable called result, which is true. So remember, this result is local to the function. So basically I'm saying that, okay, look, by default, assume it's a prime number. But if you find a factor, declare that's not a prime number. So declare false, break out from the loop because no point searching further. and return the result. So this is quite logical. I can run this once here. So it takes a while first time to run, but once it runs, then I'll be able to use this function even in other cells. So now it's ready. I can just create, let's say, for example, a new code cell, and I can then go and say is, say, for example, is prime, for example, 29, right? If I run this, I expect a true, and indeed that is true, right? If I try, for example, 290, well, definitely that is a false, because 29 times 10 is 290. So, you can actually verify with more examples, but we are quite sure that this algorithm is correct. It's doing its job, which is to tell you if the number being supplied as an argument, is it a prime or not a prime. So we have a correct algorithm at hand. Obviously, this can be improved, this can be optimized. But before going in that direction, let us first quantify how much work is our algorithm actually doing. How is this computation scaling as, let's say, the number being supplied becomes large. We're going to do that in the subsequent videos, but I hope you're finding this interesting. Now, this video is part of the Algorithms and Olympiad track, where we are studying algorithms in detail. Look at our website www.ybyte.in to understand more and enjoy programming. Take care. Thank you so much. Bye bye.